Helicoprion. Picture a shark. Now remove every tooth and replace them with a circular saw blade that spirals inward like a clock spring, coiling 150 teeth into a perfect geometric whorl the size of a dinner plate. For over a century, no paleontologist on Earth could figure out where on the animal's body that saw was located. Some said the tail. Some said the snout. The truth, when it finally came, was far worse. This is Helicoprion, the spiral saw, and it lived approximately 270 million years ago in the shallow tropical seas that covered what is now landlocked Idaho. The first fossil whorl was recovered by Alexander Karpinski in the Ural Mountains of Russia in 1899. He named the animal Helicoprion, mounted the saw on its snout like a chainsaw, and published his reconstruction with confidence. Over the next 100 years, at least 12 competing reconstructions were published. Some researchers said the whorl curled from the tail. Others placed it projecting forward from the lower jaw like a jousting lance. Nobody agreed. Nobody could prove it. The animal had become paleontology's most embarrassing open question. The resolution came in 2013, when Leif Tapanila of Idaho State University applied CT scanning to a three-dimensional specimen held at the Idaho Museum of Natural History. The scans were unambiguous. The whorl sat inside the throat, embedded deep in the lower jaw cartilage, with the teeth curving inward and downward so that anything passing the lips was drawn toward rotating blades. Not a weapon, an internal processing machine. The paper was published in Biology Letters of the Royal Society, and scientists who had spent careers arguing about the snout went very quiet. Here is what makes it genuinely disturbing. Every shark alive today sheds its teeth constantly, cycling through thousands of replacements across a lifetime. The conveyor belt of expendable teeth is one of the most successful designs in vertebrate history, 450 million years of refinement. Helicoprion abandoned it entirely. Every tooth it ever grew was permanent, locked into the spiral forever. As new teeth erupted at the base, older ones were pushed inward, rotating deeper into the coil. The outermost teeth on the whorl were the oldest and smallest. The innermost were the newest and largest. The animal was, in a very literal sense, eating time. Its entire dental history was stored in a single geometric object inside its throat. Fossil whorls have been recovered from Idaho, Russia, Nevada, Greenland, and Japan. At least 150 specimens are known globally. Not one of them includes the rest of the body. Helicoprion was a shark-like fish whose skeleton was made of cartilage, and cartilage decomposes. The whorl is composed of dentine, the same hard mineral as teeth, which is why it survives while everything else vanishes. We are looking at the one non-decomposable piece of an animal whose entire body has been erased from the record. Every reconstruction you have ever seen of the full creature, its shape, its fins, its proportions, is an inference. A guess wearing the costume of science. The largest known whorls suggest a total body length of 3 to 4 meters, comparable to a modern bull shark. Helicoprion belonged to a group called Eugeniadontida, an entirely extinct order of shark-like fish with no living relatives and no clear evolutionary descendants. They appeared in the early Permian with the whorl already fully formed. There is no transitional ancestor showing a simpler or earlier version of the mechanism. It arrived complete, fully engineered, and then vanished at the end. Permian mass extinction approximately 252 million years ago, when 96% of all marine species died. Paleontologists will tell you Helicoprion is a fascinating but explicable product of Permian evolution, a derived trait in one lineage that happened to work well enough until the world ended. That explanation is reasonable. It is also deeply incomplete. Sharks have been refining the disposable tooth row for 450 million years because it is one of the most effective solutions biology has ever found. Cambrian looked at that solution and built a clock spring instead. It never shed a tooth. It never needed to. And then it disappeared, taking whatever logic produced it entirely out of the world. Some researchers ask whether the whorl was also a display structure, partially visible during threat postures or mating rituals, its geometry too elaborate for pure function. Others note that the Permian seas were warming and acidifying in the lead-up to the Great Extinction, and wonder whether this animal's bizarre anatomy was the response of a specialist creature to a dying world, an evolutionary gamble in the final chapter. We may never know. What we know is that for 100 years, professional scientists could not determine where one bone sat inside one animal. And the answer, when it came, was a rotating saw blade in the throat. From the Permian seas, we move 300 million years earlier to the same ancient seabed that produced some of the strangest life forms ever documented, and to an animal that scientists had completely backwards, literally upside down and facing the wrong direction, for 30 years. Hallucigenia. In 1977, a Cambridge paleontologist named Simon Conway Morris stood before his colleagues and unveiled a reconstruction of a tiny Cambrian animal he had formally named that year. The name he gave it meant bizarre dream. He had it upside down. He had it facing the wrong direction. And the blob he identified as its head was fossilized gut contents oozing from its tail. Science accepted the reconstruction for 14 years before anyone caught the errors. And when they finally found the real head in 2015, what they discovered inside it was more unsettling than the mistake had been. Hallucigenia sparsa lived approximately 505 million years ago in the sea that would eventually become the Burgess Shale, a cliff face in the Canadian Rockies of British Columbia. Charles Walcott first collected specimens there in 1912. Conway Morris described and named the animal in 1977 in a paper that reconstructed it walking upright on 7 pairs of paired tentacles with stiff spines projecting above it like a defensive canopy. It looked like a walking cactus with aspirations. In 1991, Lars Ramskjöld and Ho Xiangguang demonstrated that the entire animal was inverted. The spines belonged on the back as armor. The tentacle legs belonged underneath. Conway Morris had the whole thing flipped. Then, in 2015, Martin Smith of Cambridge and Jean-Bernard Caron of the University of Toronto published a study using scanning electron microscopy on the head end, which had always appeared as a dark smear that researchers assumed was decay. The microscopy revealed a circular mouth ringed with a single row of teeth, and behind the mouth, lining the throat itself, a second set of recurved needle-like teeth pointing backward into the esophagus. Not jaw teeth, throat teeth, a ring of inward-facing needles positioned so that anything entering the mouth cannot be pushed back out. The study was published in Nature, and it remains the most complete picture of Hallucigenia's anatomy that science has ever managed. The body measures between 0.5 centimeter and 5.5 centimeters in length. It has 7 pairs of clawed legs, mismatched in size. It has those dorsal spines, which some researchers have suggested were hollow and possibly capable of delivering venom, though this remains unconfirmed. And it has a throat lined with backwards-pointing teeth that function as a one-way valve. Approximately 109 specimens of Hallucigenia sparsa are known from the Burgess Shale. A second species, Hallucigenia fortis, was identified from the Chengjiang fossil beds in Yunnan, China, suggesting the animal had at least some geographic range. Hallucigenia is now placed tentatively as a stem group panarthropod. a distant relative of modern velvet worms and through them of arthropods. Which means this upside-down backwards nightmare with a toothed throat is, in some technical sense, an ancestor of spiders and crabs and insects. Evolution took this design, apparently decided against the throat teeth and the paired spines, and rebuilt the entire body plan from scratch into something manageable. The throat teeth appear in hallucigenia and then simply vanish from the lineage. Where that adaptation went is an open question that no researcher has satisfactorily answered. Mainstream paleontologists will say hallucigenia is a well-documented example of Cambrian morphological experimentation. The explosion of body plans that occurred between 540 and 520 million years ago produced extraordinary anatomical diversity, most of which did not survive. Hallucigenia is strange because we are comparing it to the survivors, not to all the other experiments that ran alongside it. The scientific errors in its reconstruction reflect the genuine difficulty of interpreting compressed soft tissue fossils, not anything anomalous about the animal itself. But here is what that explanation does not address. The Cambrian explosion produced the major animal body plans present on Earth today within a geologically instantaneous window of roughly 20 million years, with no clear transitional ancestors preceding them in the fossil record. Hallucigenia does not appear with a series of simpler, less toothed, less armored precursors showing gradual development. It appears fully constructed in the opening pages of complex animal life. Stephen Jay Gould argued in Wonderful Life that most Cambrian designs were not failures. They were simply unlucky. One mass extinction, one geological accident, and hallucigenia's body plan might have been the one that survived, and ours might have been the cautionary footnote. The Burgess Shale preserved these animals through a rare and specific geological accident. Without it, hallucigenia would be completely unknown to science. Which raises the question of how many equally impossible animals left no trace at all, and how much of our confidence about Cambrian life is actually confidence about one lucky cliff face in British Columbia. Tully monster. It is the official state fossil of Illinois. It has been collected in the thousands from a single fossil bed south of Chicago. It has been studied by professional paleontologists for nearly 70 years, photographed, CT scanned, and subjected to the most advanced imaging technology the 21st century offers. 2 separate research teams published their findings about it in Nature, the most prestigious scientific journal on Earth, 3 years apart. They reached opposite conclusions about what kind of animal it is. The Tully monster does not just resist easy classification, it resists classification entirely. The animal lived approximately 307 million years ago in the shallow delta system that would become the Mazon Creek fossil beds of Will County, Illinois, now buried under a reclaimed strip mine landscape south of Chicago. Francis Tully, an amateur fossil collector and pipeline worker, found the first specimen around 1958 while digging through the ironstone nodules the area was famous for. He brought it to the Field Museum of Natural History in Chicago, where curator Eugene Richardson formally described it as Tullymonstrum gregarium in 1966. Gregarium means common because the beds produced them constantly. Workers had been finding them for years without knowing what they had. Richardson could not place the animal in any known phylum. He listed it as Problematica, the paleontological designation for an organism that cannot be classified within any established group. 52 years passed. Then in 2016, a team led by Victoria McCoy of Yale published in Nature, claiming Tullymonstrum was a vertebrate, specifically a jawless fish related to lampreys based on what they identified as gill structures and a notochord running the body length. The paper made international news. Illinois' bizarre state fossil had finally been placed. Except that in 2019, a separate team published also in Nature, systematically dismantling every vertebrate claim. The supposed notochord was a digestive tract. The supposed gill pouches were misidentified structures. The authors concluded Tulamonstrum was an invertebrate of uncertain and possibly unprecedented affinity. The Illinois state fossil is, as of today, still unclassified. The body ranges from 7 to 35 centimeters across known specimens. The front of the animal extends into a long, flexible proboscis, accounting for roughly 1/3 of its total length, tipped with a small claw-like grasping structure. The eyes sit on rigid lateral stalks projecting from the sides of the head, like a hammerhead shark's eyes, but mounted on stiff rods rather than flesh. A transverse bar divides the body roughly in the middle, its function unknown. The tail bears a fin. Over 6,000 specimens have been collected from Mason Creek. Every one of them shows these same features. Not one of them tells researchers what the animal fundamentally was. The Mason Creek Formation preserves soft tissue in iron carbonate nodules through a process that captures organisms within hours to days of death, providing extraordinary anatomical detail. This should make classification easier. The fact that it is not should give us pause. The eye-on-stalk configuration is unique in the entire fossil record at this scale. It matches neither arthropod optics nor vertebrate optics. The proboscis structure has no confirmed parallel. And the transverse bar that divides the body is a feature with no modern analog that any researcher has convincingly identified. Paleontologists will say this is a preservation challenge, not a mystery of biology. Soft tissue introduces interpretive ambiguity. Given enough time, new specimens and better imaging techniques will resolve the classification. The two contradictory Nature papers reflect the inherent difficulty of working with compressed material from an unusual organism, not a fundamental gap in our understanding of animal evolution. But two teams, with access to identical material and the best technology available, published contradictory findings in the world's most respected scientific journal. At some point, the phrase interpretive ambiguity becomes a polite way of saying, we do not know what this is. Some paleontologists have suggested Tulamonstrum may represent a lineage that arose, thrived by the thousands in one specific ecosystem, and went extinct without descendants, without precursors, and without anything in the existing record that provides a reference frame for understanding it. Not a proto-vertebrate, not an invertebrate, something that was its own category briefly and then ended. The state of Illinois put this animal on an official fossil designation, which means it appears on educational materials, classroom posters, and museum plaques across the state. Most of those materials describe it with confident language that the research itself does not support. The Tully monster is more honest than that. It sits in its ironstone nodule and declines to be explained. Opabinia. In 1972, paleontologist Harry Whittington stood before the assembled Oxford University Symposium on Paleontology and presented his reconstruction of a new Cambrian animal. The audience laughed, not politely, not briefly. They actually laughed out loud because what Whittington was showing them was so anatomically absurd that many present assumed the reconstruction was a mistake. 5 eyes, a flexible trunk ending in a claw, a mouth that faced backwards. Whittington waited for the room to settle. Then he explained that every element of the reconstruction was supported by the fossil evidence, and that the laughter was, in a very real sense, the appropriate response to what the Cambrian had produced. Opabinia regalis lived approximately 505 million years ago in the same sea that gave us Hallucigenia, buried now in the Burgess Shale of British Columbia. Charles Walcott collected the first specimens in 1912 but never formally described the animal. Harry Whittington of Cambridge undertook the landmark re-examination of Burgess Shale fauna throughout the 1970s, formally redescribing Opabinia in a 56-page paper published in the Philosophical Transactions of the Royal Society B in 1975. That paper remains the definitive treatment of the animal to this day. No major new specimen has substantially changed the picture Whittington drew. Approximately 20 complete specimens are known from the Burgess Shale. None have been found anywhere else on Earth. The anatomy reads like a description assembled from mismatched components. 5 compound eyes, arranged in 2 pairs plus 1 unpaired central eye, all on stalks above the head. A flexible proboscis extending forward from the front of the head, roughly as long as the body itself, capable of bending backward underneath the animal to deliver captured prey to a mouth that faces rearward. 15 body segments, each bearing a gill lobe on top and a locomotion flap below, giving the animal 30 independent moving parts along its underside. The proboscis terminates in a spined, claw-like grasping structure. To feed, Opabinia had to seize something with a forward-facing claw, bend its entire neck backwards beneath its body, and pass the prey to a mouth pointing the wrong direction. This is not an approximation or an interpretation. This is what the fossils show. Opabinia is now placed tentatively as a stem group arthropod, a distant branch of the lineage that eventually produced insects, crabs, and spiders. Conway Morris and Budd argued in 2003 for a close relationship with the anomalocaridids. Others have placed it outside arthropods entirely. The 5-eyed, backwards-mouthed, claw-trunked animal has resisted a clean taxonomic home with the same stubbornness it resisted the credulity of Oxford. What is not disputed is that it belongs to no living group and left no confirmed descendants. It appeared in the Cambrian, survived long enough to be preserved 20 times, and was deleted. The standard explanation is that Opabinia was a stem group panarthropod that lost the evolutionary competition during or after the Cambrian. The surviving body plans, those that gave rise to arthropods and worms, proved more robust across subsequent mass extinctions. Opabinia's design was not inferior, simply unlucky. The small number of known specimens may reflect either genuine rarity in life or a preservation gap. But consider the design itself for a moment. 5 independent eyes processing visual information in 5 streams simultaneously. A proboscis that can reach behind the animal's own body. 30 independent locomotive flaps. This is not a rough draft. This is an animal of considerable mechanical and sensory sophistication, operating 505 million years ago, in what paleontology insists on calling the dawn of complex animal life. Stephen Jay Gould wrote that the Cambrian was not a ladder of progress toward modern life. It was a lottery. Most of the tickets lost. Opabinia held one of the losing tickets, but nothing about the design itself explains why it lost. 20 specimens, 1 cliff face, 1 mountain range. Some researchers ask whether Opabinia was genuinely rare in life, or whether this is what the fossil record looks like when preservation conditions almost never align. If that question applies to Opabinia, it applies to everything else in the Cambrian we think we understand. The laughter in that Oxford lecture hall in 1972 was the sound of scientists confronting the gap between their models and what the Earth had actually produced. It is arguably the most honest sound in the history of paleontology. From the Cambrian, we descend through time into the Devonian, and to an apex predator so powerful that the scientists who measured its bite force checked their instruments twice. The most disturbing detail about it is not what it had. It is what it didn't. Dunkleosteus. It had no teeth. Let that register. The apex predator of the Devonian seas, 6 meters long, armored in interlocking plates of bone, had no teeth at all. Instead, it had self-sharpening bone blades that generated a bite force of more than 8,000 pounds per square inch, more than a great white shark, more than a saltwater crocodile, more pound for pound than almost any predator that has ever lived on this planet. And the most unsettling detail, the one that gets quietly omitted from museum plaques and documentary narration, is this. We have no idea what the rest of its body looked like. Unclassifiable terrelli was formally named in 1873 by John Strong Newberry, based on specimens recovered from the Cleveland Shale, a geological formation exposed in creek beds south of the city of Cleveland, Ohio. The animal was later renamed in honor of David Dunkel, a vertebrate paleontology curator at the Cleveland Museum of Natural History, which holds some of the finest specimens known. It belongs to the class Placodermi, the armored fish that dominated Earth's seas during the Devonian period, roughly 358 to 419 million years ago. The Cleveland Museum holds at least 5 associated skull specimens. They are extraordinary objects, massive, complex, and deeply strange. The jaw mechanism of Unclassifiable operated via a 4-bar linkage, 2 separate mechanical joints opening simultaneously, allowing the mouth to fully open in approximately 20 milliseconds. Philip Anderson of the University of Massachusetts Amherst and Mark Westneat of the Field Museum of Natural History published their bite force analysis in Biology Letters in 2006, calculating the force at approximately 4,400 newtons at the front of the jaw and up to 5,300 newtons at the blade tip, equivalent to roughly 8,000 pounds per square inch. The blades themselves are projections of the facial bone plate grown directly from the skull. As the upper and lower blades wear against each other in use, they self-sharpen, a system that never dulls and never needs replacement. There is no living fish with anything remotely like this. The skull of the largest known specimen measures approximately 87 centimeters in length. Based on comparative scaling from other placoderms, total body length estimates range from roughly 6 to 8.5 meters. Those estimates exist because the armor plating covers only the first third of the animal. Everything behind the shoulder girdle is cartilage. Cartilage decomposes. The complete body shape of Unclassifiable terrelli has never been confirmed by a single fossil. Every full-body depiction ever published is an inference modeled on the proportions of smaller, fully preserved placoderms. In 2023, Umberto Ferron of the University of Bristol argued in a published study that Unclassifiable was likely more tuna-shaped than previous reconstructions suggested, fast and stiff-bodied rather than slow and bulky. The previous consensus reconstructions may have been substantially wrong. 60 skulls found, 0 complete skeletons. There is also the matter of the stomach contents. Fossilized gut material from Ohio specimens contains partially digested remains of other Unclassifiable individuals, skull plates folded and compacted in a pattern consistent with regurgitation of indigestible armor. This animal was eating its own kind. Paleontologists read this as opportunistic behavior or population stress, a top predator consuming its own species when other prey became scarce. Either interpretation implies something about the state of the late Devonian ecosystem in which these animals lived. Mainstream paleontology explains Unclassifiable as the peak predator of a thriving Devonian marine world whose extinction at the end Devonian mass extinction approximately 359 million years ago was simply part of the catastrophic loss of roughly 75% of all marine species. The self-sharpening bone blades are an elegant and efficient solution to the problem of durable dentition, and the lack of postcranial fossils is straightforwardly explained by differential preservation. Nothing mysterious. Just physics and time. But the entire class Placodermi, every armored fish lineage, was deleted at the end Devonian and never re-evolved. No subsequent vertebrate has independently reinvented dermal armor as a primary defense, despite 70 million years of apparent success. Why has a design that dominated the seas for longer than dinosaurs ruled the land never returned? We reconstruct the most powerful jawed fish in history from 1/3 of its skeleton, and then we place it in museum halls with confident labels. Dunkleosteus looks back from its armored skull and tells us nothing about what came after its throat. Arthropleura. The largest land invertebrate in the history of Earth was not discovered through deliberate excavation, triumphant announcement, and years of careful preparation. It was identified through a set of footprints left in ancient mud that turned to stone 315 million years ago. Scientists knew it existed. They knew roughly how large it was. They spent over a century finding only fragments. Then, in 2021, a geology student on a beach in Northumberland, England, tripped on a fallen sandstone block, looked down, and found the largest Arthropleura specimen ever recorded staring back at him from the broken stone. Arthropleura armata was a myriapod, a member of the same group that includes modern millipedes and centipedes. It lived during the Carboniferous period, approximately 315 million years ago, in the vast coal forests that blanketed the equatorial regions of what is now northern England and Nova Scotia, Canada. Arthropleura was first described from fragmentary cuticle material and trackway impressions in the 19th century. The Joggins Fossil Cliffs in Nova Scotia, now a UNESCO World Heritage Site, contain parallel paired trackway impressions roughly 50 centimeters apart, attributed to Arthropleura locomotion. For over 100 years, the animal was known primarily through what it left behind on the ground rather than what it left of itself. The student who found the Northumberland specimen was Jamie Jordan, studying at Newcastle University. The block had recently fallen from a sea cliff at Howick Bay, cracked open by wave action, and revealed a 75-centimeter fragment of articulated exoskeleton, approximately 55 centimeters wide. Neil Davies of the University of Cambridge led the formal analysis, published in the Journal of the Geological Society in January 2022. Based on the fragment's dimensions, Davies and colleagues estimated the total animal at 2.63 meters in length, weighing approximately 50 kilograms. The largest land invertebrate that ever existed. And had that block fallen into the sea rather than onto the beach, it would have been ground to sediment within weeks. 2.5 meters. Compare that to the largest living millipede, Archospirostreptus gigas, which reaches 38 centimeters at maximum. Arthropleura exceeded this by a factor of roughly 6.5. The reason this size was possible then and is impossible now is atmospheric oxygen. The Carboniferous atmosphere contained approximately 35% oxygen compared to today's 21%. Invertebrates breathe through passive diffusion across their body surface. In an atmosphere with 67% more available oxygen than today, diffusion reaches deeper into larger bodies, enabling sizes that would cause modern invertebrates to suffocate under their own mass. Arthropleura is not just a large animal, it is a measurement of how different the air once was. Despite its size, Arthropleura appears to have been herbivorous. Material from one German specimen contained fern spore remains and plant cuticle consistent with a diet of carboniferous vegetation. This means the largest land invertebrate in Earth's history was not a predator, but a living conveyor belt moving through the understory of coal forests, consuming ferns. How it shed its enormous exoskeleton, a process all arthropods must undergo to grow, remains entirely unclear. No shed cuticle deposits of this scale have ever been found in Carboniferous coal measures, which is itself a strange absence for an animal that left so many trackways. Something this large, molting in a forest, should have left evidence. It did not. Paleontologists will say Arthropleura is a well-understood product of Carboniferous hyperoxia, and when extinct at the end of the Carboniferous approximately 299 million years ago, when the coal forests collapsed and atmospheric oxygen declined. The ecology explains the size and the extinction explains the disappearance. These are accurate statements as far as they go. But the complete anatomy of Arthropleura remains unconfirmed. We do not know with certainty how many legs it had. We do not know what its head looked like in full detail. We do not know the mechanics by which it moved 2.5 meters of articulated body through dense undergrowth without destroying itself. The Howick Bay specimen was revealed by a geological accident within a window of weeks. What the cliff face had held for 300 million years was nearly lost to the tide. Some researchers ask how many other Arthropleura specimens have already been destroyed by the sea before anyone could look down at the right moment. From the coal forests of England, we cross the Atlantic and move forward in time to South America, where isolation produced something that should not have been possible. An animal that nature, according to all our models of evolutionary probability, had already built on another continent and had no logical reason to build again. Thylacosmolus, the saber-toothed cat, is one of the most recognized icons of prehistoric life. Long canines, muscular shoulders, the predatory crouch. We know this design. We recognize it because it recurs, because it works, because evolution arrived at it and kept it. What rarely gets discussed in any serious depth is that nature built this design at least 3 separate times on different continents in completely unrelated lineages. And the South American version, the one that grew from marsupial stock in complete isolation, had bone scabbards extending from its lower jaw to sheathe the blades when its mouth was closed. The true saber-toothed cats never thought of that. Thylacosmolus atrox lived in South America during the Miocene and Pliocene epochs, roughly 9 to 3 million years ago, in the open grasslands and shrublands of what is now Argentina. It was formally described by Elmer Riggs of the Field Museum of Natural History in Chicago in 1933, from specimens collected in Catamarca Province in northwestern Argentina. The specimens are held in the Field Museum collections. Thylacosmolus belonged to Sparassodonta, an extinct order of metatherian mammals, meaning it was more closely related to modern opossums than to any cat. It was not a cat, it was not related to a cat. The saber-tooth anatomy evolved in it entirely separately, on a continent that had been biologically isolated from North America and Eurasia for approximately 30 million years. The upper canine teeth were ever growing. This is the detail that sets Thylacosmolus apart from all Machaerodontine felids, the true saber-toothed cats. A Smilodon's canines grew to adult size and stopped. Thylacosmolus's canines grew continuously throughout the animal's life, rooted in dental tissue that never ceased producing tooth. This created a structural problem. Where do you put teeth that keep getting longer? The skull responded by developing enlarged flanges on the lower jaw, bony projections curving forward to form a sheath, protecting the canines when the mouth was closed. The tooth roots extended upward through the skull above the level of the eye sockets. The entire anterior portion of the skull was architecturally organized around the management of 2 perpetually growing blades. Christine Argot's detailed study of Thylacosmolus postcranial morphology, published in the Zoological Journal of the Linnean Society in 2001, found robust forelimb musculature suggesting powerful grappling behavior, a wrestling predator that restrained prey with its arms before deploying those canines. A biomechanical analysis using CT scanning, published in the early 2020s, and examining jaw mechanics in detail, found that Thylacosmolus had a comparatively weaker bite force than similarly sized placental carnivores. This raises a question the field has not fully resolved. If the canines could not anchor in bone or penetrate thick hide through raw bite pressure alone, how did the animal use them? Some researchers now suggest a throat-slashing methodology, the forelimbs controlling the prey while the canines were drawn across soft tissue rather than driven through it. A cut, not a stab. A different engineering solution to the same problem of killing large animals. South America was an island continent for roughly 30 million years, isolated by the Atlantic's widening and the absence of a land connection to North America. Sparassodont carnivores evolved independently to fill every ecological niche that placental carnivores filled elsewhere. Thylacosmolus was that continent's answer to Smilodon, its answer to the apex predatory mammal built from marsupial raw material by 3 million years of completely independent selection. When the Isthmus of Panama formed approximately 3 million years ago and North American placental carnivores entered South America, Thylacosmolus went extinct within roughly 1 million to 2 million years. Whether competition drove the extinction or whether climate change was the primary cause is still debated. The mainstream explanation is elegant: convergent evolution. Unrelated lineages independently arriving at similar functional solutions to identical ecological problems. Flight in birds, bats, and pterosaurs. Eyes in vertebrates and cephalopods. Saber-teeth in nimravids, machairodontine felids, and sparassodonts. The logic is coherent. It is also, in its way, deeply strange. Simon Conway Morris argued in Life Solution that convergence on this scale suggests evolution is navigating toward a limited set of stable functional forms, that the space of possible biology is smaller than random mutation would predict, and that certain designs keep being reinvented because they represent attractors in the landscape of what works. The saber-tooth appears to be one of those attractors. 3 separate lineages, 3 separate continents, the same blade reinvented in bone again and again, as if something in the structure of predation requires it. Titanoboa. The dinosaurs had been dead for 6 million years. The mass extinction that ended the Cretaceous had scoured the world clean, and the survivors were rebuilding in the silence left behind. Into that silence, in what is now northern Colombia, crawled a snake the length of a school bus, weighing over 1,000 kilograms, living in a rainforest so hot that our thermal models for reptile physiology say it should have been impossible. Titanoboa therijonensis is not just the largest snake ever found. It is physical proof that the Earth once operated on rules we do not fully understand, and its bones were sitting inside the world's largest open-pit coal mine, waiting for someone to recognize what the workers had been finding for years. The Charajan Coal Mine in La Guajira Department of Northern Colombia is the largest open-pit coal mine on Earth, and it is also, unexpectedly, one of the most important Paleocene fossil sites in the world. The formation dates to approximately 58 to 60 million years ago, roughly 6 million years after the end Cretaceous impact. Jonathan Block of the University of Florida and Carlos Jaramillo of the Smithsonian Tropical Research Institute led the team that identified the animal. Mine workers had been encountering oversized vertebrae for years, assuming they were from large fish or fossil crocodilians. Block recognized them as snake vertebrae of extraordinary dimensions. The formal description was published in Nature in 2009. The numbers are difficult to absorb. Total body length estimated at 12.8 to 14.3 meters, based on scaling from vertebral diameter. The largest reliably measured modern anaconda reaches approximately 8.8 meters. Titanoboa exceeded this by roughly 60%. Body mass estimated at approximately 1,135 kilograms, over 11 times the mass of the largest living snake species. Individual vertebral centra measure up to 10 centimeters across. The vertebrae are so large that when Bloch first examined them, his initial instinct was that the scaling was wrong, that the measurements had somehow been corrupted. They had not. Over 180 individual snake specimens were eventually recovered from 28 localities within the mine. Titanoboa belongs to the family Boidae, making it most closely related to modern boas and anacondas, which means that the lineage still exists today. Modern boids simply do not grow anywhere near this large, and the reason connects directly to the animal's most disturbing implication, the paleoclimate reconstruction of Paleocene saragon, derived from leaf shape analysis and stable isotope data, gives mean annual temperatures of 30 to 34 degrees Celsius, roughly 3 to 4 degrees warmer than the hottest modern tropical rainforests. In the same 2009 Nature paper, Head and colleagues used the known relationship between body size in large tropical snakes and ambient temperature to back-calculate the Paleocene climate from Titanoboa's dimensions. The snake was so large that it forced an upward revision in the temperature estimates. The animal's existence was itself a thermometer. The world was hotter than previous models had assumed, and Titanoboa was the evidence. Paleontologists explain this cleanly. Warmer environments allow ectotherms to sustain larger body sizes. Titanoboa lived in a world hotter than anything alive today, experienced no ecological competition from the large predators that had just been wiped out, and grew to fill the available space. When global temperatures cooled through the Eocene and subsequent epochs, maximum attainable body size for snakes decreased accordingly. The logic is sound. The saragon fauna surrounding Titanoboa includes giant turtles, large crocodilians, and lungfish, all confirming an extraordinary ecosystem running on post-extinction excess and greenhouse heat. But the question that the mainstream framing tends to skip past is what the existence of Titanoboa tells us about projection, the conditions that produced it, a world resetting after mass extinction, elevated atmospheric temperatures, collapsed ecological competition, suppressed predator diversity, bear a structural resemblance to scenarios currently being modeled for the planet's near future. Titanoboa is not a curiosity from deep time. It is a data point about what biology does when given the right conditions. Some researchers ask, somewhat uncomfortably, whether the Paleocene was not an anomaly in Earth's history but a preview, and whether the animals we think of as the upper limit of possible scale were simply scaled to a temperature we have not yet re-reached. We may never know how large a boid can grow if the world gets warm enough. Titanoboa suggests the answer is larger than we are comfortable contemplating. Predator X. There is an island so far inside the Arctic Circle that the sun does not rise for months and does not set for months. Polar bears outnumber people. The ground is permanently frozen. And in the rock beneath that frozen ground, laid down in a warm, shallow sea 147 million years ago, there is a skull nearly 2.5 meters long, belonging to an animal whose bite force, when calculated by the team that measured it, exceeded that of Tyrannosaurus rex by a factor of 4. The creature is formally known as Pliosaurus funki. It was discovered on Svalbard, a Norwegian archipelago at 78 degrees north latitude, roughly halfway between the Norwegian mainland and the North Pole. The first bones were found in 2006 by amateur fossil hunter Bjørn Funke during an expedition led by Jørn Hurum of the Natural History Museum of the University of Oslo. When the team extracted the first large vertebra from the permafrost, Hurum initially thought they had found a dinosaur. They had not. They had found something that lived in the sea, and the sea in question was the late Jurassic Arctic, which was, at that time, a warm and shallow tropical body of water supporting one of the densest concentrations of large marine reptiles known from the fossil record. The animal was nicknamed Predator X by the media before formal description. The name Pliosaurus funke was assigned by Roger Benson of Oxford University and Patrick Druckenmiller of the University of Alaska in a paper published in the Norwegian Journal of Geology in 2012, honoring Bjørn Funke's discovery. The specimens are held at the Natural History Museum of the University of Oslo. Two separate partial skeletons were excavated across multiple field seasons. Neither is complete. The skull measures 2.4 meters in length. For comparison, the skull of a fully grown Tyrannosaurus rex measures approximately 1.5 meters. The bite force was estimated by Gregory Erickson of Florida State University at approximately 33,000 pounds per square inch, compared to T-Rex at roughly 8,000 pounds per square inch and a great white shark at approximately 4,000 pounds per square inch. Individual teeth measured up to 30 centimeters in length. The four flippers were each approximately 3 meters long, equal in size fore and aft, giving the animal the underwater flying locomotion used by sea turtles, but scaled to a body estimated at 10 to 13 meters total length and a mass that some researchers have placed at 45 tons. The jaw of Pliosaurus funke could, by the biomechanical modeling, have bitten clean through an animal the size of a modern orca. The question that nobody has satisfactorily answered is what required that. What was living in the Jurassic Arctic that was large enough, or armored enough, or dangerous enough to have driven the evolution of the most powerful jaw in the history of vertebrate life? The Slotsmoya member of the Agard-Fjelle Formation, where the Svalbard specimens were found, has produced an extraordinary density of large marine reptile fossils, including ichthyosaurs, long-necked plesiosaurs, and other pliosaurs. Hurum's team has published evidence from bite marks on contemporaneous marine reptile bones showing systematic dismemberment behavior, not random ambush strikes but patterned processing of prey. Something that large, operating with that force, apparently had a method. Mainstream paleontology places Pliosaurus funke at the apex of pliosaur evolution, a well-understood group of Mesozoic marine reptiles that trended toward increasing size through the Jurassic. The extreme bite force reflects the mechanical consequences of extreme skull size. Nothing about its anatomy is anatomically unprecedented for a pliosaur. Only scale distinguishes it. But Jørn Hurum has stated publicly that new Svalbard specimens are emerging from melting permafrost faster than his team can excavate them. The thawing ground is releasing material that has been locked in ice for tens of millions of years, and the window for extraction before erosion destroys it is narrowing every field season. Some of what is currently emerging from the Arctic may be larger than what has already been found. Pliosaurus funke is one of the rare prehistoric animals being actively revealed by climate change, and the race between scientific capacity and the melt rate is, by several accounts, one that science is currently losing. Anomalocaris. 520 million years ago, in the first chapter of Complex Animal Life, the dominant predator of Earth's oceans had eyes containing 16,000 individual optical lenses. Modern dragonflies, the most visually acute insects alive today, have roughly 30,000. Horseshoe crabs, one of the oldest living arthropod lineages on the planet, have approximately 1,000. For a creature living in what paleontology calls the dawn of animal complexity, in what the textbooks describe as a primitive era, Anomalocaris had eyes that were not primitive at all. By almost any optical measure, they were better than most things alive on Earth today. And the scientists who published that discovery in a 2011 paper in Nature spent considerable time checking whether their measurements were correct before they submitted. The discovery of those eyes came from the Emu Bay Shale on Kangaroo Island, South Australia, where exceptional preservation conditions captured the stalked compound eyes of Anomalocaris in enough detail for John Patterson of the University of New England and his colleagues to count approximately 16,000 individual lenses per eye, arranged in a hexagonal array consistent with what optical engineers call an apposition compound eye, the same fundamental design used by modern dragonflies, mantis shrimps, and horseshoe crabs. The eyes are stalked, projecting from the sides of the head, each several centimeters in diameter, proportionally enormous relative to the body. Whatever Anomalocaris was tracking in the Cambrian Sea, it was tracking it in high resolution. The animal itself has one of the most tangled discovery histories in paleontology. Its name means abnormal shrimp because the first fossil fragment found, the grasping frontal appendage, was described in 1892 by Joseph Whiteaves as the abdomen of an unusual crustacean. The circular mouth disc was separately described as a species of jellyfish called Peytoia. The full body, integrating both structures into a single animal, was only recognized by Harry Whittington and Simon Conway Morris during their landmark reanalysis of the Burgess Shale fauna in the 1970s and 80s. For decades, the jellyfish, the shrimp, and the body had been cataloged as three different organisms. Anomalocaris was assembled from its own misidentified pieces. The complete animal reaches up to 1 meter in length in typical specimens, with some researchers estimating the largest species at closer to 2 meters. It was 10 to 20 times larger than most of its contemporaries, a size disparity comparable to a single elephant in a room otherwise occupied by mice. The frontal appendages have articulated segments lined with sharp inward-facing spines. The circular mouth is a flexible ring of overlapping plates. Multiple species of Anomalocaris have been identified from Cambrian fossil beds on 5 continents, from Canada to China to Australia to Greenland to the United States, making it one of the first genuinely global animals in the fossil record. Anomalocaris belongs to Radiodonta, an extinct order now placed as a stem group arthropod. Its lineage apparently persisted until at least the early Devonian, approximately 480 million years ago, meaning it survived the end Cambrian extinctions and continued for at least 40 million additional years before disappearing from the record without confirmed descendants. Paleontologists will explain the sophisticated compound eye as the product of strong selective pressure on a pursuit predator operating in a 3-dimensional marine environment. High visual acuity offers decisive fitness advantages. The eye is advanced, but it evolved through the same mechanisms as every other Cambrian adaptation: selection for function in a competitive ecosystem. The Cambrian explosion was, in this reading, simply a rapid evolutionary radiation driven by ecological competition, and Anomalocaris benefited from being among its earliest large-bodied participants. But the compound eye of Anomalocaris does not appear in the fossil record with a series of transitional, less complex precursors showing gradual development. It appears fully formed, fully optimized, in the Cambrian's opening pages, carried by an animal already the largest thing in the sea, already globally distributed, already operating a mechanical body plan of considerable sophistication. Andrew Parker of the Natural History Museum in London proposed what he called the light switch theory, the idea that the Cambrian explosion was itself triggered by the evolution of the image-forming eye. Before eyes, survival required only chemical sensing. After eyes, every organism that could be seen became prey, and every organism that could see gained an advantage. Parker's argument is that Anomalocaris was not a product of the Cambrian explosion. It was one of its causes. An animal whose eyes made the world more dangerous for everything else, and in doing so, accelerated the evolution of shells, armor, speed, and camouflage across the entire animal kingdom simultaneously. The eyes of Anomalocaris stare back at us from 520 million years ago, and the question they are actually asking is not what did it see. The question is what changed when something first began, truly, to see. 10 creatures, 500 million years of fossil record. And the thread connecting all of them is not size, not danger, not even extinction. It is the specific quality of their impossibility. Each animal on this list breaks something: a rule of anatomy, a timeline of evolution, a model of what the ancient world was supposed to be capable of. Helicoprion breaks the tooth, Hallucigenia breaks the orientation, the Tully monster breaks classification itself. Opabinia breaks every assumption about what a functional predator should look like. Dunkleosteus breaks the jaw and hides the body. Arthropleura breaks the size ceiling for land invertebrates and leaves nothing but footprints. Thylacosmolus breaks the boundary between marsupial and apex carnivore and invents the blade twice. Titanoboa breaks the thermal ceiling and forces paleoclimatologists to revise their models. Predator X breaks the bite force record inside the Arctic Circle. And Anomalocaris breaks the assumption that sophistication is something evolution works towards slowly because it arrived fully constructed before the story was supposed to have started. Science has an explanation for every one of them: convergent evolution, Cambrian explosion, hyperoxic atmosphere, differential preservation, post-extinction ecological vacuum. These are real mechanisms. They are not invented. But notice what each explanation does. It describes how the animal was possible and leaves the deeper question entirely untouched. Why does evolution keep arriving at the same designs independently? Why did the Cambrian produce optical sophistication before the gradual process should have allowed it? Why did the Permian produce a dental mechanism so singular that it has never appeared again in 400 million years of subsequent life? The mainstream answers are accurate as far as they go. They just don't go very far. The fossil record is not a complete library. It is a collection of accidents, the rare moments when conditions aligned precisely enough to preserve something that should have decomposed and vanished completely. Every animal on this list survived into our knowledge by geological chance. The Hallucigenia specimens exist because of one cliff face in British Columbia. The Tully monster specimens exist because a pipeline worker looked down. The Arthropleura specimen from Northumberland exists because a block fell onto a beach instead of into the sea, which means the record we have is not the record of what existed. It is the record of what was lucky enough to be preserved. And the gaps between the luck are full of things we have not found yet. Most people walk past museum displays and see dead animals behind glass. They read the placard, accept the label, and move on. You followed the buzzsaw into the Permian. You followed the 5 eyes into the Cambrian. You followed the bone scabbards into Patagonia and the 1,000-kilogram snake into a Colombian coal mine. That means your mind is doing something most people's minds refuse to do. It is holding the question open instead of closing it. This channel exists for exactly that, not for comfortable answers, for the precise moment where the comfortable answer stops working and something more interesting begins. Hit subscribe and lock in your access to the archive. Then go to the comments and tell me which of these 10 animals disturbs you most and not the biggest or the most lethal. The most disturbing. The one that makes you feel like the rules are different than we were told. Make your case. The floor is yours. These creatures were not monsters. They were solutions, evolution's answers to questions the world was asking in chapters of time so deep that our entire written history is a footnote in the final paragraph. They lived, they were real, and they were erased so completely that we reconstruct them from a single bone, a single track, a single fossilized eye, the buzzsaw in the throat, the five-eyed dream, the animal with no name and no phylum, the jaw that left no body. The Earth does not announce when it changes its rules. It simply runs the next experiment and waits. These were 10 of the results. The question is, how many more are still buried, waiting for someone to look down at exactly the right moment? Hit subscribe. The next excavation starts now.